Did you know that submarine cables can listen to the areas around them and share data about what is happening on the ocean floor? Well, this is Telegeography Explains the Internet, the show that explores the business behind all of the ways that humans stay connected around the world. And I'm your host, Greg Bryant. Our show today is the final in our mini-series all about submarine cables, where we will explore the rapidly evolving technology of using fiber optic cables as remote sensors to identify potential issues and gather data we otherwise would never be able to have access to. To guide us through this, my guest is Mark Englund, the CEO of Fibersense. Mark explains the fascinating world of distributed acoustic sensing and how this emerging technology is turning existing fiber optic cables into sentient, continuous sensors. We explore how this is transforming the submarine cable industry, providing unparalleled real-time protection by detecting anchors, fishing gear, and other potential threats. Mark details how Fibersense uses machine learning to cut through the ocean's cacophony and make the data actionable for cable operators. Finally, we spend a little time looking beyond the subsea, exploring the immense potential of DAS, or Distributed Acoustic Sensing, for terrestrial fiber in applications like protection against excavators, water leaks in city infrastructure, and even a new vision for traffic safety and autonomous vehicles. As always, please like or rate the show, subscribe, tell a friend to listen, and of course, feel free to find me on LinkedIn with suggestions and feedback. Enjoy the show. Welcome to the show, Mark.
Thanks, Greg. Great to be on.
Yeah, absolutely. It's always exciting for me when we're talking about submarine cables that you are on, basically the antipode, the other side of the world for me, and we're having this live conversation. I love that. It still feels like magic to me, even after all these years.
Through the submarine telecom cables. That's right. We're talking about today.
Yeah. Absolutely. Yeah. All right. So Mark, before we jump in, could you give the audience a brief background on yourself and how you came to be the CEO at Fibersense, please?
Absolutely. So I am a proper nerd, straight up. Born really interested in technology from the get-go. I had a mother who was sort of saying, hey, it's weird that you want to read the video cassette recorder instructions, not once, but 3 times.
You're in the right place, I can tell you that. So, yeah.
So since the get-go, I'm an engineer. So I trained in physics, engineering applications, but specifically optical fiber sensors, which is the topic of today, for sonar applications in the mid-90s. So I have a defense science background. I spent my early years at the Defense Science Research Organization in Australia called the DSTO, and also spent time in the US at the Naval Research Laboratory in the late 90s, which was absolutely mind-blowing. So that technology, optical fiber sensing over fibers, was the genesis of what we're talking about today. It was very early back then. That was being applied to basically use light traveling down a piece of fiber to hear sound. So light to hear sound was the soundbite in 1997. And so the telecom boom happened that applied the essence of that same technology base. That went through in 2000, 2005, 2010 was really the peak of that. And literally trillions of dollars worth of investment into the components of photonics, like the science of light, for telecoms. And where we ended up with is in the sensing area, that was also incredibly lifted by that investment. So all the component technologies, the cost, the performance dramatically improved. And so that's what we have today is the optical fiber sensing platforms have evolved orders of magnitude in terms of their capability and performance from those early research years in the late 90s. So that's my background. I started a company in 2000 to apply a type of filter in amplified, basically in repeaters, to mitigate long distance signal distortion. That company I sold to Subcom, one of the 4 submarine cable manufacturers around the world, in 2010. And I spent the next 5 years basically within that organization, and the parent company extolling the virtues of the telecom model is about to change. So it's about the old days with AT&T, and the new model that was about to drop was the era of cloud and the hyperscalers, so Google, Facebook, Microsoft, as it was back then. So I spent that until 2015, and then this startup bug, which I've had on my whole life, kicked back in, and Fibersense, the business we're talking about today, is really the intersection for the first time of optical fiber sensing technologies, which was the genesis of the whole optical fiber technology area, meets the telecom infrastructure that's been
Right.
built over the last 20 years. So it's optical fiber sensors allow us to be able to convert that enormous piece of infrastructure that we built around the world that we just take for granted today, that is making stuff like this call happen, and every other aspect of our digital life that we take for granted today is all powered by this physical infrastructure that's in the oceans and in the ground. And all of that optical fiber, every meter of it, when we are talking about billions of route miles of cables in cities, interstate, and in the oceans that connect the countries, every meter of that infrastructure can be converted into an optical fiber sensor.
Yeah.
I'll go on to say.
That is incredible, and certainly it's not taken for granted here at Telegeography, because of course we're in the capstone here of a series we've been doing on submarine cables. Of course, always I have the submarine cable map over my shoulder, right? So and that's our goal here is for the audience, even within the telecom industry, who take this infrastructure for granted. We want to dive deeper on it and really understand it. And I thought this was a fitting, final episode in this little mini series that we're doing, because even though you're saying this is coming to us from the late '90s, it still feels kind of cutting edge. You know what I mean? That we're exploring some new capabilities in this space. So I want us to first really back up, and you've touched on this a bit already, but could you give us the kind of cable sensing 101? Like, what does that actually mean? What are you actually able to do in terms of sensing with cables?
Well, let me then back up a little bit further still, which I think is an important aspect of understanding the context and the capability that this technology represents. So sonar, sound navigation and ranging, was effectively invented to allow submarines midway through last century, really, where they came to the fore, to navigate underwater. So that's basically closing your eyes and then using your ears to navigate through an environment. So sound is a very special medium. Everything that moves, almost everything that moves, there's very, very few things that don't emit a sound field when they move. Mm-hmm. And that sound field encodes a couple of things. One is what the object is, and then two, what it's doing. So that's the 101 of sonar. Optical fiber sensing over telecoms infrastructure allows you to import that capability on very, very large continuous apertures. And we're talking thousands of kilometers here, the stuff that's in that map in the back of you. That capability allows a cable, which was traditionally hauled off the side of a ship and never seen again unless it was broken and needed to be repaired. So it goes dark. It's one of the few assets, particularly in the deep oceans. Like, littoral surveys are common, but there's not too many companies that know what's happening at 6,000 meters midway through the Pacific, or for that matter, the Indian Ocean or the Atlantic. So it's a dark asset. Now, we virtually know nothing about the ocean floor in terms of survey in a percentage sense. So this capability allows you to turn on perception stacks, not just I can hear sounds. It's the same analogy that I like try and convey it. If you want a sense of this, it's like go to the traffic lights that you're about to cross as a pedestrian, close your eyes, and work out just with sound what you can perceive. And it's quite high. And so you very rarely see crashes. You hear them first, and then you're cued to look at them. So that's really the analogy on this. Optical fiber sensing meets telecom cables. It allows us to put in sonar capabilities. So we detect sounds from objects and events. That sound field allows us to determine what the object is, so classify, and then work out what the object is doing, so the kinetics or the dynamics of that situation. So you can really get quite detailed views. And one example I think you were talking about, touching on with me, was we did unfortunately a pedestrian fatality reconstruction terrestrially. So we were in cities, we're in an area, and in that unfortunate case, the police had no idea what exactly happened at the point that pedestrian was struck. And we happened to have a system along the road in that area. And with just listening to the sound that was recorded, we could work out how fast the pedestrian was walking prior to impact, how fast the vehicle that hit the pedestrian was traveling, not at the point of impact, but all the way back to 6 kilometers up the road prior to hitting the pedestrian. Then working out what the car that hit the pedestrian did after the impact, and then identify all eyewitness vehicles that went through. And that was all done through a cable listening to the sound field around the highway. So that's the type of forensic capability that we bring into the submarine telecoms industry at a very important time in the history of not only the threat vectors, which are significant in building, but also how important these cables are. And I won't wax lyrical to you on that, because I know you know that better than anyone, but there's two axes going on here in the submarine telecom space that I think this type of capability provides perception at really granular details for us to be able to deter, to intercede, or we call interdict around the asset, or even after the fact to be able to follow up with accountability about what happened, because we've got data now. When it's not just speculation or circumstantial, there's quantifiable data that you could actually take to prosecute.
Yeah, man, you raised so many interesting points that I want to kind of put a pin in before we move along, which is, first, I think to emphasize when you talk about that pedestrian example, it strikes me that there's multiple layers of the technology here. First, there's just the ability to do this acoustic sensing, but then, as you described, there's the interpretation of those sounds, so that you have this technology to understand what it is you're hearing and reconstructing there. And obviously we can take that to the submarine cable space and know the difference between a fishing net dragging on the seafloor and an anchor, and it's never sharks, but maybe a shark, and that sort of, right. But then, also at the same time that all of this is happening, those cables are already just there transmitting lots of data, right? This is just an additional sort of benefit that we get of having that infrastructure in place, right?
Absolutely. You touch on a couple of aspects of it. That the light that's traveling down this fiber is not only transmitting enormous amounts of information that are absolutely critical to this new digital world, generative AI, the whole future that looks incredible as far as the technology perspective goes, but there is a lot that infrastructure can do on the ocean floor. I would probably defer to you. How many miles of subsea cable are on the ocean floor today? It would be.
Oh man, that is not a statistic I have off the top. Some of my colleagues would, I can tell you, but I mean, yeah.
I know the subcom folks very well, and
yeah.
Something on the order of over 1 million miles of discrete cable.
Yeah, that's easily believable. Yeah.
And like one of the things I'll just pull in for context is we're also being affiliated with the NOAA in the US, the National Oceanographic and Atmospheric Administration, a great team up in Seattle that protect the world from tsunamis. They've made an industry effectively around how do you put a tsunami warning sensor on the ocean floor mid-Pacific. It's not trivial. And these dartboy technologies today, about $1 million US a piece, at least back in 2015 when I looked at this. And they've got a very important job to do, which is to basically detect the presence of a tsunami post an earthquake, which doesn't always happen. So you don't want to be evacuating Honolulu on a false alarm. That's incredibly expensive and disruptive.
Costly, yeah, absolutely.
So I just mentioned there's another aspect of the telecoms and the sensing is that there's a lot of import around these oceans really matter to us. They matter to us from a natural disaster standpoint. They matter to us from a food source. They matter from a climate driver. There's a lot of other things that this type of sensing technology can do with this infrastructure on the ocean floor. And that's really I think why you're looking at something that's changing quite quickly with fiber sensing coming in is the cost of putting that dart buoy on the ocean floor is $1 million US. We can put the equivalent sensor on the ocean floor on a couple of channels that can do that type of sensitivity at that location for 2 orders of magnitude less cost. So this is existing infrastructure can be reconverted, and the cost of any sensing system going into the field is dominated by the physical sensors and the telemetry. And we already have that in the water. The glass in these optical fiber cables acts as the transducer, in our case, the telemetry system, and the power source. So, there's I don't think we've seen anything yet. I mean, I think the penetration of fiber sensing into the subsea telecoms industry today would be less than 1%.
Really interesting. Okay,
it's small.
Well, that's why we need to have you on. So yeah,
absolutely. I mean, it's starting. I mean, we just come back from Submarine Networks World last week in Singapore, and fairly record interest in this area. Like, it's taken a long time for the industry to understand it. B, that if I put this stuff on my cable, is there any risk introduced to the relay? And that's a very important issue in the subsea industry. And then C, does it actually deliver anything that warrants the service cost that we would have? And that curve's taken about 4 years to really land. Like, we've got use cases, examples. We've had a couple of launch clients, absolute gems of Southern Cross Cable Networks, the early adopter in this space, and they've got a history of doing this. They have got strong relationships with companies like Sienna. They're connected with some of the very first hybrid models where it's not just SLTs provided by the usual suspects of Subcom, Alcatel, NEC, Fujitsu. When Sienna and Infinera came in, Southern Cross were the early adopters in that space, and they were exactly the same with us. They saw this as the future, and Dean Beverker in particular, if you're aware of him, he's an incredible statesman in the industry. I really admire. He's on the ICPC as well, the International Cable Protection Committee, and I think Southern Cross was a very important breakthrough for them to adopt us. Has really been the beginning of this being taken seriously. That we can do.
Yeah, then you can start to build some real ROI data and things like that, right?
You got it. And that's the next segue. Is this isn't easy to do. I wish I could say we should have been doing this a decade ago. But there's a couple of aspects of this, and there's this. If you just try to sell the sensing boxes, which is the traditional model, it's the most straightforward in terms of, if you want to develop a business in distributed fiber sensing, that's the easiest model, is that you design, develop a sensing box, and you sell the sensing box to a cable owner, and off they go. And the big issue with that is this technology really does need machine learning and AI because it's sensitive to everything. Like, we literally see, when these cables are live on the ocean floor, we see all ocean noise. So with the surface waves, biologics in the background, in brackets whales, other biological entities that make noises, every ship, vessel in the water, and a lot of other effects as well, like the microseismic background, pressure waves owing to swell, and so you've got all that cacophony. So it's literally like being in a really, really, one of those dinner parties where there's a lot of wine flowing and everyone's talking 1,000 miles an hour, and
you have to pinpoint to the one thing that's valuable to know.
Yeah, and
exactly.
There's a lot of signal processing going on in your head in that situation to try and isolate. And so the analogy here is that you need a lot of data in different scenarios for a classifier to work in an automated way that can be trusted. So the key terms are false positives, false negatives. So I'm telling you there's a vessel there. I'm telling you there's an anchor drag there through the digital system, and you need to be able to trust that. It's like the boy who cried wolf. If this is a false positive too many times, the value of what you're providing drops dramatically. And so that is the Achilles heel of the industry, is everyone goes out and they do a demonstration, and it's like, oh my god, this technology is amazing. And then they set it to work. They connect it to the operations team, and then in the first couple of months, they see 200 to 300 false positives, right?
Alarms all the time, and so then
And
it just becomes signal to noise.
that
Yeah.
gets tired really quickly,
Right.
and in some cases, it's just switched off. So that has been the history of some of the areas of applying optical fiber sensors, or distributed acoustic sensing, more particularly with what we're talking about today. But so we have a service model, and the primary reason for that service model, when we sell or we connect to our clients, we don't sell them the box. We install the box, and then we run the system for the client and then deliver the actual insights. And what that allows us to do is to build the data ocean. Like, unfortunately,
Right.
the data lake, probably a better term. Data lake,
Yeah.
and that data lake is absolutely critical to getting to where we are today, which is we're in the range of 1 to 3% false positives,
Wow.
1% false
Yeah.
negatives. So that
Hmm.
that level is defense grade. Like, you can actually behave, you can act on that. Like, you interdict, you can go and chase shit down. You can get to site quickly and do a survey. And if you couldn't get to that level, then you won't be queuing very expensive assets. There's not many times you're going to send out a boat and there's nothing there. So
Right. Right.
I'll stop there.
So you're really not the OEM, so to speak, here of just selling a box and then the cable operator does something with that box, but rather you're doing the monitoring service, identifying what sounds are a threat, and I assume that's both sort of preemptively and post fault as well.
That's right. Now, there's a couple of different time frames. So firstly, it, the technology curve to get up in interpreting this, like a sonar operator sitting in a submarine, it's
Right.
decades of training to get to the point where you're listening to something and you know acoustically what that is.
Yeah, speaking another language,
It's
basically,
totally
right?
another
Yeah.
language, and it's
Yeah.
learnable. Like, we've got people in our
Mhm.
business today that it's bizarre. They can look at these acoustic images and
Yeah.
read it like text. It's incredible
Yeah.
to watch. Like, these are
The
guys that
Matrix. Yeah.
tens of thousands of hours of staring at these things. They
Yeah.
get pretty good at understanding. Anyway, but that the client can't get there. That's just going to be not practical for them to spend, go and train someone up for that period of time. So we take all that out. We really drop the technology curve dramatically. They don't need an engineer specialist in the business for this. They literally just need someone who can understand the context of these objects and events around the cable. So what should we do, for example, if we're detecting an anchor drop close into the cable in territorial waters? What do we do if there's an anchor drop in an EEZ zone off the cable? What if there's a crayfish pot boat that's detected that now we've got a physical contact with the cable? It's that level that we're now operating at, and I think that really changes the gearing. Like, the customers can go from zero to those type of analysis panels in 30 days. Like, it's not a long. So I think that's a really important aspect of the service as well, is that the bar to being able to engage this type of deep tech quickly is lowered. And I think that the last part is I'm sort of thinking about the model of the data flows, is really around, if we get the service into the clients and it's up early, they can integrate it further up into their processes. So like, we have an operations center and they have an operations center, and they lock arms pretty quick. And so we have the perception stack turned on, so lights over the asset now. And the operations team that have the effectors, that could be a phone call to a ship, or it could be something going to site, which increasingly we're seeing, that linkage works pretty well. We've got a service operations center. So stop there.
Yeah, so there's a sort of chain of events that an alarm triggers, and that process has to be built in to the operational standards of the cable. So are you saying that maybe it's better to do this to some degree during the cable build process, but I assume you can also adopt this to an existing cable as well, right?
Yeah, no, I actually missed one of your questions. It just reminded me. So there's we talk of three time time zones. We talk real time, so stuff that happens that
Mm.
we've got to react
Hmm.
to immediately. An example would be ship coming through. We're detecting what we call a seabed interaction event. That does not mean we've got a cable contact yet, but there's
Right.
contact with the ocean floor happening in proximity to the cable, which is a high risk proxy, an
Right.
early warning event, basically. So those things are communicated real time to our cable clients. And then there's other events that are on that cable that are just as big a deal, but they're much slower in gestation. So,
Mm.
for example, one of the things that we stumbled on by accident really was we can detect cable strumming really easily. So particularly on a steep incline coming off maybe a Pacific island that goes deep quickly, we see a lot of suspended cable situations where the cable is basically off the ocean floor between 2 points.
And so
And
it's
so
so it's kind of taut, basically. Yeah.
basically like a guitar string, and
Yeah.
the tide
Yeah.
basically strums that. And so
Hmm.
you've now got like a harmonic motion effectively going on
Wow.
that cable, and it's
Interesting.
just a matter of time before the metal in that cable heads into shunt fault conditions. So that's a known precursor to shunt fault, this cable strumming. We see that really easily. The other side of it is so that's we call this PED. So it's prosecution, exploitation, dissemination. It's like what time zone? PED one is real time. PED two is after the event.
Mm.
Maybe on the
Hmm.
order of a month, you could scan that type of event and be okay. A couple of
Right.
months, and then there'll be a maintenance process to go do that. Or maybe there's an event that's undefined, and we used to have a lot of these in the early years, and increasingly with the machine learning and training processes, that's diminishing, but we still get them. So that would be one that we process on the order of maybe 3 months is to make sure that the algorithms understand these new edge cases. It's a little bit
Right.
like full self-driving. Like there's
And
always
can assign those to a particular problem or something to look out for and that sort of thing.
there's stuff that's happened around these cables is truly bizarre. We've had crayfish pots dropped off, in the right place, and then the tides have basically dragged the
Mm.
crayfish pot slowly
Hmm.
towards the cable and then snagged the cable, which is a big problem.
Right.
It's only a matter of time there that you'll have a fault as well. So you have this evolving signal over weeks and we've no idea what this is. It looks like a snail on the ocean floor that weighs
Yeah.
200 kilos. Uh,
Right.
no, anyway, so those things. I mean,
Which would be an interesting discovery for biological science as well,
it
right? So,
would, but
yeah.
wrong way. But I mean,
Yeah.
that was only verified, what we call labelled, because our
Hmm.
divers went down to the cable where the signal source
Ah,
was, and went, "That's a crayfish pot." And so
that's really interesting.
the
Yeah.
algorithm gets upgraded, and now we're
Yeah.
seeing crayfish pots in quite a few of the cable clients on the basis of that learning process. So we are continuing to do that. And that's another advantage of staying connected to our clients through the life of the or life of the cable in a lot of cases. So
Right.
yeah, I think more and more there's maintenance advantages, and there's
Hmm.
um, interdiction opportunities. There's culpability, ships going over the top, turning off the AIS. We might have caught that vessel several months ago when it had its AIS on. We
Oh, could
caught
you explain what that is for folks not that familiar with the maritime world? Yeah, no, please. Yeah.
I have to say, Greg, I don't remember the acronym, which is pretty embarrassing. But it's basically an RF beacon on a ship. Let me see.
That lets a central sort of
Automatic.
database know where every ship in the
That's right.
world is
It's
currently
just like
located.
RF beacons on aircraft that are routinely
Yeah, I
used.
don't remember what it means either, and I should. So that's not on you.
I just
Yeah.
looked it up. It's automatic information system.
Gotcha. Okay.
Marine
Yeah.
vessels around the world have this system on board, and it's designed to basically stop collisions and keeping everyone
Hmm.
aware of what's happening around them. But those vessels can.
The ships can toggle those on and off themselves, right? So.
That's right. I mean, that's where it gets murky. Is a
Hmm.
vessel that is typically doing something that they don't want anyone else to see.
Right.
spatially, they flick it off. So
Right.
one big advantage in this technology that we're talking about today is that we don't rely on that. Like we see the acoustic information of that vessel directly, and just like
Mm-hmm.
your
Mm-hmm.
voice, there's a fingerprint to it, and that
Right.
fingerprint is
Mm-hmm.
unique enough that we can identify
Mm-hmm.
specific
Mm-hmm.
vessels through that fingerprint. And so if you get an AIS label, so an AIS was on, so we know now the vessel's name, the tonnage, where it's going, who owns it, and that same vessel comes back with the AIS off, but we detected the acoustics, then we
Right.
know it's that vessel. So we've been seeing that more and more as one of the key use cases is that vessel drops an anchor, AIS is off, it trawls through, cable's broken, we're doing the identification.
Right. So you have a culprit, sort of, and I'm sure there's certain probably companies or ships that might be problem ships in this sense, and that's really interesting. I liken it to I did my graduate school work in geography, and was at the University of Maryland, just near the Goddard Space Center. So lots of remote sensing of a different kind, right? And we did I did a camp in graduate school all about ground truthing, where you would pick an image of 10 square meters of forest and go down and measure the trees in person, and compare that to the satellite imagery. Sounds like you are doing some sea truthing, as it were, instead of ground truthing, and relating it. And that's how those satellite images that we have now give us so much data, because we've related it to what you can actually see in the ground. You can extrapolate from there. So I can really sort of grasp onto
Yeah,
how important it is to have this ongoing utilization of this technology, growing the data set. You're feeding that into the machine learning tools, and it's going to just become more and more accurate,
better
right?
and better. Yeah,
Yeah,
better
absolutely.
classifications, more nuanced
Hmm.
threat vectors, that type of thing. Yeah,
Yeah.
I mean, there's been a lot of media around so-called grey warfare, and I do
Hmm.
think that the media's taken that too far in
Yeah.
majority, not always, but in majority. There's a bit
Hmm.
too much speculation. But there are some.
Everybody always wants to that's a headline grabber, and it's not to say that it's not a real issue, because it very much is, but it's usually something else, right? So
Yeah,
yeah.
so some of the pushback from, I mean, there's certainly parties within the subsea industry that, in my view, are too far the other way, which is,
Hmm.
there's nothing going on here. And I don't think that's true either.
Yeah, we live in a chaotic world sometimes. Yeah,
But
so yeah.
but enter the age of, like, let's stop speculating and start using the
Hmm.
data and sensing
Right.
technologies to end up with, in God we trust, and everyone else bring data. Like, literally,
That's
let's
right.
stop the speculation, bring the data. And
Hmm.
I think
Hmm.
that's where we're going. And there's also a perception in the industry that's worth just raising here, and it's boiled away online on LinkedIn, and which is, look, sensing on submarine cables won't stop these events. And
Right.
like, whilst that's true in some sense, it's not true in all senses. Like,
I was
there-
gonna
there's
say the strumming, for example, that you talk about. That's one where you might be able to make some changes, or if the AIS system is engaged, and you could find out whose crayfish pot is close to your cable. There could be some mitigation here, not just after the fact, right? So yeah.
or basically one of the anchor events happens, whether
Hmm.
it's deliberate or otherwise, we don't know, but
Right.
it went across. But now we have clear evidence of anchor contact with the cable
Hmm.
and ship fingerprint. So we know what vessel did that. I mean,
Right.
some of the conjecture online was, well, and I'm like, radar in World War II, there were very similar comments made about it. It's
Mm.
just
Hmm.
a whiz bang technology.
Right.
It won't replace the fighters, the fighter pilot's skill and the guns and the aircraft. Well, all
Right.
that's true. Uh, Adding intelligence or perception to any scene is very valuable. And
Hmm.
today, I mean, the case in point is there is no aircraft today that's not either illuminated
Right.
by radar or has radar on board itself.
Hmm.
And so this perception stack, it just wasn't possible to do this in the industry up until distributed fiber sensing arrived.
Right.
And now those cables are becoming sentient as the first step, which is just capable of detecting what's around them.
Hmm.
And then the intelligence builds over the top of that. And I don't think anyone would argue down the road more intelligence around these assets will allow for better decisions and less grey behaviors around
Yeah.
these cables, I guess is the point. So, yeah.
Yeah, yeah, absolutely. Again, even if it's an after the fact understanding of what happened, that can inform the whole industry on how to mitigate these things moving forward.
That's right.
Uh, Mark, I want to, before we go any further, do talk about the what are the current limitations of distributed acoustic sensing, Daz, and if you see some way of breaking through those current limitations, and sort of the given those distance limitations that Daz has, what's the impact of the utility still?
Okay. Well, the first one was cost. Not much of an
Hmm.
issue today, I contend, because companies like us that have chosen to be vertically integrated, um, the cost of the unit when we first started to put a node on a shore end would be of order a couple $100,000 US. It was quite a big
Right.
number.
New technology is often like that,
Yeah.
right? Yeah.
And it was big and ungainly. It was all that computer
Yeah.
stuff. Like here's the first one. It was a full rack, basically the first
Hmm.
DAS systems. The current generation of DAS system is 3RU, so it's a small rack mountable device. But so cost was a big issue back in 2015. I don't think it's as bigger issue today. It makes the economics around subsea cables. I think we're almost there in that frame, so that's improved a lot. The length of interrogation is another pretty hot topic in this space now that everyone's becoming awake to the utility and the application of it. So typically first repeater, we're at first repeater today. In general,
Hmm.
there are cases where we're out to the second and third repeater. So
Hmm.
that's a length limit. So typically it's
Right.
interrogated from shore. There are other sensing technologies I should raise today that the industry is looking at. So state of polarization is a forward propagating sensing capability. We are a reflective system, a bit like radar.
Right.
And there's also interferometry in the classic optical fiber sensing case that goes forward propagating as well. State of polarization and interferometric sensing can see through the entire cable. If you
Oh
go
wow.
trans-Pacific or
Yeah.
transatlantic. The big distinction, though, is the length resolving power of those sensing types is very limited. So you have a
Mm.
signal. There's something happening on the cable, but localizing
Where?
where it is
Right.
might, in some cases, be down to 70, 80 kilometers. So that might be
Hmm.
okay for an earthquake detection event.
Right.
But for an anchor drag event that you want to respond to, that's just not
Just not
practical.
granular enough. Right. Yeah. Hmm.
Um, so I think really with us, we're resolved at 5 meters
Wow.
length.
Hmm.
So we're a much tighter capability. We're also phased array capable, if that term lands with you or the listeners. It's the same
Hmm.
technology they use in radars for sweeping the way that the group of
Mm.
channels across the fiber look spatially in azimuth. So
Hmm.
that beamforming technology is something that DAS has. So we have much greater fidelity but limited length is the position, Greg. And without letting the cat out of the bag, I think that's going to change materially in the next couple of
Hmm.
years to the point where it is actually full system, not
Wow.
just
Okay.
not just.
Full system with the kind of granular 5 meter granularity that you're talking about, right? So I
That's
mean
right.
that's huge for the submarine cable industry. It's also, we'll get to this maybe later, but huge for science, right? Huge, so many things that we, as the saying kind of goes, we know more about outer space in
That's
many
right.
respects than we do about the
We're going
oceans,
forward.
right? So yeah, absolutely. And so then just to put a pin in that, and to be clear too, that when you're talking about being able to have this level of granularity with DAS to the first, second, or maybe even third repeater,
Yeah.
uh, I've been doing, I'm not the submarine cable expert at telegeography by any means, but I've been doing this little series, and I know now that, of course, that is where the vast majority of cable interactions happen, right? So
Yeah.
yeah,
No,
yeah.
we fell on our feet. It wasn't by design, I
Mhm.
have to say, Greg, but that's a fact in the industry. Is most of the
Yeah.
I'll call it standard risks up until this notion of grey warfare has arrived in the industry. The standard risks are predominantly in that first repeater range. Maybe the second repeater, but typically 80. It depends on who you talk to. But ICPC would say over 80% of those risks exist, and it makes sense because it's the littoral section. Right. That's the most shallow. So when you're 6,000 meters, there's not too much man-made stuff that can even get to you at that point if you're trans-Pacific. And that's what we rely on, by the way, for these networks to be sustained over the 25-year lifetime that they're putting in the water. So
absolutely. And there's just a physical geography constraint here, right? So one thing I love to show people who aren't familiar with the industry is an overlay of the submarine cable map and the shipping channel map, right? And of course, submarine cables are going to go ashore in places where we already have shipping channels and whatnot, right? So that overlap happens there. When you get into the wider ocean, in our actually previous episode in the series was all about routing, and of course, where does the routing become difficult? It's nearest to the landing station, right? So
I forecast at this point cautiously is that we'll have that high fidelity resolution. In fact, we're doing it today. There's 2,000 landings approximately, depends on who you talk to today in the water. And we aim to light up a significant fraction of that. And then I think the second wave for these technologies will be the forward propagating, but DAS-like fidelity. And as you say, marine scientific research, cable protection over the full length of the system. There are examples. We have a couple of examples that are outliers where the fish attraction devices that are put into deep water snag a cable in deep water. And so you need to be looking at something mid-span in that case. So it could be mid-Pacific or mid-Indian Ocean. They're edge cases at the moment, but I think they do need to be covered. As I say, the criticality of this infrastructure going down. Right. There was a really interesting article in the UK Parliament that was just released on their analysis of the criticality of subsea cables around the UK and just how important it is. It's not just a case of inconvenience when these cables go down en masse. You're talking life effect, life-threatening type outcomes.
Yeah, not even just economic impacts, but literally our lives depend on connectivity now. Absolutely.
Medical, logistics, transport, everything is impacted when the digital infrastructure is impaired properly.
Yeah, absolutely. Yeah. So I think that's a good call to action right there for the industry of why to look into and consider this technology. I want to close out because we're running out of time here with just a quick review of some of the other things that Fibersense does. We've been all focused on the submarine cable industry because that's what the series we're doing here is. But I do understand that you have a lot of other potential applications for, if you're saying there's millions of kilometers of submarine cables, then that is tenfold at least terrestrially around the world where we have built out fiber. Pretty much, as I like to tell people who aren't familiar with this, anywhere that you see poles or really anywhere that you see a road, there's very likely fiber, down much of that infrastructure, right, across the entire world, because it gets to at least the curb in most places in the developed world now, right? Australia, for example, a big effort, NBN, to get fiber literally all over the country, almost anywhere where there are people living, right? So we have all that fiber there sitting there. What is the potential for your technology to utilize that?
Yeah, it's I've had a couple of different startups, and this particular startup, the curse that came with it was it applies to almost anything that moves in a terrestrial or marine context. And well, that sounds good. You have to focus. And we 2016, the thought experiment occurred that let's try and light up a piece of standard telecoms optical fiber across the city. There were a lot of early naysayers that said you just won't see anything. It's in a trench. It's sitting in conduit. It's not ideally laid.
The city is noisy.
It's ridiculous. What are you talking about? Anyway, so we lit this up, and we were very fortunate to have the support of quite a legendary entrepreneur in Australia called Bevan Slattery. He heard about this idea and went, "That's interesting. Could we borrow an optical fiber, Bevan?" And he was like, "Go for it." So we ended up doing a trial across Sydney in 2016, way ago, like 9 years ago,
Yeah.
and lit this thing up. We were in an Equinix data center, SY2, I think it was, in the south of Sydney. And I distinctly remember this first night turning it on and watching these waterfalls flow. So this technology is continuously, so 50 kilometers across Sydney.
Right.
It's 5 meter resolved, and we have this time axis down the vertical, and we have this absolute cacophony coming down the screen. And we could see pretty much everything. It was a bit of an epiphany that sort of individual vehicles moving up the road, pedestrians walking up footpaths, trains moving in subways, sirens going off in ambulances. That was the beginning of it. So we shut the doors on the business,
right,
and patented this because it's the first reapplication of a very important piece of infrastructure in the world. And after that, we had 30 ideas for what we would do with it. But we ended up focusing on what had actually a commercial case that we could engage immediately, technically close. We didn't have to do too much, raise too much money or anything like that. So we started in asset protection. So that's critical infrastructure protection, very similar to what we're talking about today in subsea infrastructure. It's how we got into it, actually, because we came in through protecting the terrestrial cables from not anchors, excavators.
Right.
In
so there's a lot of that. As someone who's worked a lot with enterprise networks, anybody, that is one of the first questions always is, can I get my carrier to give me my KMZ file, KMZ file, right? And understand, that I have actual diversity, because it's always happening that there's a backhoe or someone drives into a telephone pole.
Sometimes those cables aren't diverse. I mean, there's a whole range of things like that. So that's a standard product. We call that digital asset, and that's been sold to hyperscalers and carriers around the world today. And then the adjacency, I'll get to the pedestrian in a second, but the adjacency that sounds not that exciting, which is turning out to be absolutely key to this scaling out of our network infrastructure, sensing network infrastructure across cities, is water leak detection and mitigation. So we're actively in cities. You can also hear water leaks, believe it or not, through these cables. And there's a lot of work that's gone into that, many years. But we have an algorithm now that's capable of detecting these leaks reliably. And that's a tremendous step forward for the water industry.
You don't wait for the sinkhole. You can head that off the pass, right? Yeah,
exactly. The issue that happened in Singapore, there was another one recently, I think, in Hong Kong. Those are the type of events. Like you've got some problem going on with either drainage or a water main or a distribution system that goes up. So that's a big focus. We do a lot of water leak, and you'll be hearing from us at least about that in a pretty big way in 2026, 2027. That becomes a full division unto itself. And then the most sexy piece of what we do is it's a very new capability of detecting individual vehicles, not with equipment on the car. Like that's the conventional wisdom, is to put 5G transceivers and telemetry and stuff. The problem with that approach is you need every vehicle to have that instrumentation on it if you want to see all vehicles. And we get around that by listening passively to the signals coming off the vehicles. We don't care whether it's electric or it's a 1968 VW Beetle, which I've got. It doesn't matter. You'll hear that signature, and you can individually resolve where that vehicle is, and you can track the vehicle down the road and through the grid and through the. So that's what was applied to that pedestrian fatality reconstruction I mentioned to you. That's post-event. But there's a lot of other stuff that we can provide. So, for example, in comes full self-driving. The regulator bodies are like, what's that like? It's an autonomous vehicle. Waymo in San Francisco. I don't know where you've done that, but it's a mind-blowing experience for a techo.
Absolutely, yeah.
So in that, Waymo's moving around the traffic, and the regulators are only relying on what the Waymo is telling them happened. But we provide the ability to look down in a bird's eye view of all those vehicles moving around that autonomous vehicle in real time. So The perception
And
stack.
that in turn is going to feed so much more data into the autonomous driving systems, right? So that they get to know more about all the possible interactions. Right?
And as my wife would be quick to point out, the big one is, you get into a car, you switch on our system, and the system's now looking at a bird's eye view, has been looking at a bird's eye view around the area you're going to drive for the last 2 weeks. It knows what's going on in terms of traffic behavior and the edge case guy that's speeding, and there's another guy who's intoxicated, and there's another guy that's had a bad breakup. And that type of perception stack can now be brought into you as the consumer in front of a steering wheel. That you've now got a sixth sense outside the car that allows you to move the kids or whatever you're doing from home to school in a much safer manner. I mean, that's I think the holy grail for where we want to go is it's safety. Road deaths are a big deal in terms of nothing like the airline industry is so much better. But that public space is seen to be stochastic just because it's all these random actors. But you can measure it. And if you get enough detail, it starts to be predictable. And the predictability will improve the safety is how it ends.
Man, as a cyclist, I really can't wait for that world, because I feel like, especially post-COVID, man, just drivers have gotten even worse. So it's terrifying out there, and I could really see that vision of just the big problem that AI can solve for us is what to do with reams of data, but what the key to making AI useful is having quality data sources available that give you real world information that's actionable. And this sounds like a really promising future. So Mark, this has been really fascinating, and again, I hope that certainly folks from the submarine cable industry look more into this, because it sounds very promising there, but also just everyone who's interested in technology and where our world can go with all these new technologies. How can they keep up with you and Fibersense if they want to stay on top of these developments?
Our website, but we're very active on LinkedIn. We really are trying to make sure that we communicate well where the cutting edge is and how we might be able to help clients in the various industries that we're serving today. But it's our website, and it'll be LinkedIn.
Excellent. Yeah. Awesome. All right. Yeah. Everybody take a look there. I've been doing this sort of informal review of where people are getting their information like this these days. And almost everybody now is just saying LinkedIn. I think X is dead for this kind of thing. Blue Sky never took off. So that's where I'm putting most of my efforts to. Kicking and screaming, of course, because I'm not very good at it, but I'm trying. So, excellent. Yeah. Right. Well, Mark, this was great fun. I learned a lot. Thank you so much for joining us. Yeah.
Thank you. Awesome.
Cheers. Thanks for listening. Telegeography Explains the Internet comes from the experts here at Telegeography. It's edited and produced by Jane Miller, and it's hosted by me, Greg Bryan. And I also wrote that theme song you're listening to right now. To learn more about our data, jump over to telegeography.com, and we'll see you on the internet.